So the first announcement we have to make is that we are running CTF challenges, and those challenges actually started yesterday because we are doing a workshop, but for some reason nobody really wanted to do anything interactive in the workshop, and that means that the challenges are all three still unsolved. Those are smart contracts on the Ethereum mainnet. So if you look at those, and this is actually a little bit funny because somebody tried to solve the challenge, but in the process of doing so, he failed and he added even more ether to the contract. So now you can win a little bit more. And this was his second attempt, which also failed. So if you're quick enough, you can win a total of 1.5 ether, which should be around $300 worth. And you find this here on this GitHub repository. Sure, I hope you can read that. It's a Smashing Smart Contracts workshop, or just Google for it. All right, start.
I think view, and it should be full screen somewhere. Full screen.
So we are going to talk about automated exploitations of smart contracts on the Ethereum blockchain. We are both from Consensus. I'm Chief Hacking Officer, or whatever that means, at MythX, and Daniel is an auditor and researcher at Consensus Diligence, who do security audits for smart contracts. So normally we help developers to create more secure smart contracts, but we also do some offensive research because we want to stay on top of our game. There's a lot of other people who contributed in some way to this talk, and the code we are going to show. So we are going to show 4 tools today, 3 of which are introduced for the first time. And there were a lot of contributors involved, so all of this is open source. The MythX core team, the Consensus Diligence guys, Samsun, who is a very famous researcher who contributed some of his bot research, and the Ethereum security community in general, which is small but really awesome. So what we're going to cover is, first of all, symbolic execution for automatically detecting bugs in EVM bytecode. And we are going to focus on instances of bugs where the attacker steals ETH. So ETH is the native currency of the Ethereum blockchain from other contracts. So the goal is always to increase your own balance in some way. We are then going to show how to automate these exploits and basically write a script kiddie tool that you run against the contract and it will do everything out of the box. And then we are going to show how to exploit people who are using these tools by tricking them into sending you ether because they don't know what they're doing. And then on the next level, we are going to show you how to exploit people who use these tools. So it's kind of a layered approach. A very brief intro to Ethereum. Ethereum is a blockchain network and it's a distributed state machine. So you have this so-called world state, and there's a huge network of nodes and they all agree on the same state, which includes account balances. So the state includes accounts, and every account has a balance. And each time a transaction gets accepted into the blockchain, this changes the state in some way. So it might decrease one account's balance and increase another account's balance. And the network is permissionless. Anybody can send transactions, but they have to follow the consensus rules of the blockchain. So what makes Ethereum different from Bitcoin is that you have a lot more flexibility of how transactions can change the blockchain, so you can deploy small immutable programs called smart contracts, which are basically chunks of bytecode written in a simple stack-based language. And what's special about them, first of all, is they are immutable. So once a smart contract is deployed to the chain and you have consensus that this smart contract exists, it can never ever be changed. So it's much more like a real-world contract where you have a set of rules that everybody agrees to adhere to than like an app that you can update anytime later. From the view of symbolic execution, there are a couple of things that are interesting. First of all, executing instruction on the Ethereum blockchain costs gas, which is paid in Ethereum's native currency, Ether, and that's a spam protection because computation is expensive because every node in the system needs to run the same code, right? And that means that in a single transaction, you can only do a limited amount of computation, which is good for symbolic analysis because it mitigates state space explosions. So there's only a limited amount of states you have to look up. But on the other hand, the world state can be mutated over subsequent transactions. So you can basically split up your computation into little chunks, and that makes symbolic execution challenging again because you run into the traditional problems of state space explosion and so on. So brief primer on symbolic execution. Here you'll see a very simple smart contract that's written in Solidity, which is the most popular language at the moment. And the smart contract represents a cat. It has one function. And this function either extends the cat's life or it kills the cat. And there's a very interesting instruction in Solidity called self-destruct. What this instruction does is, so it was originally called suicide. So essentially, the contract is going to kill itself. It's going to delete its own code and free its storage. And send its remaining balance to an arbitrary address that you specify here. In this case, it's the 0 address. So if you look at this program, there are two outcomes that can happen, right? If this Boolean variable is true, then grant survival is false. Is true. And the cat will not be killed. We will reach a normal stop state. But on the other hand, if it's set to false, we will reach the self-destruct instructions. So these are the two possibilities that can happen. So what we do in symbolic execution now is that we, every time we reach a conditional jump, we follow down both paths and we annotate each edge on, so if you look at this as a control flow graph, we annotate each edge with the path constraints imposed by the jump condition, right? So we can say that if the first function argument is true, and this actually looks a bit complicated because that's what the Solidity compiler produces, but it ends up meaning if it's true, then the cat survives. If it's false, the cat dies. And so you could think about the cat being in both states simultaneously. And what that allows us to do now is we can ask, if we want to reach the state where the cat dies, what are the input variables we have to supply to the program? And we can do that by passing this path formula or this proposition to an SMT solver. We use set3 in Mithril, for example, and this will give us the correct input values that we need to send. And these propositions can be arbitrarily complex, right? So we can look at very complex programs that have many input variables, but we will always get the correct result. So I'm not going to go into much more detail because we actually practiced this talk a couple of days ago and it turned out to take about 3 hours to do everything. So we need to cut things down a bit. But if you're interested, there's a good execution by a good summary by my colleague Joran, talking about symbolic execution, and then there's a paper I wrote last year called Smashing Smart Contracts that goes into a lot of detail. I can also recommend this paper, Gnawing at Ethereum, and there's a lot of other stuff you can just find on Google. We'll have a few more references at the end of the talk. Right, so our symbolic execution tool is called Mithril, and it's designed with simplicity in mind. So if you want to use it, you can install it with Python 3, and you can then either analyze Solidity code files or contract addresses at either the mainnet or a testnet or whatever you like. And I'm going to show you a very brief demo of how that looks like. So this is a killable smart contract, and it has a kill function that calls self-destruct, and there's one prerequisite that we have to fulfill. So you need to be in the map of allowed addresses that are allowed to kill the contract, right? So you have to call a sequence of transactions. The first one is set allow to set this mapping to true, and then you need to set kill. And so this might look like a very simple demo, but that's actually something that happened in practice. So I think in 2017 there was a hack of the parity wallet library that in principle was very similar. So there was an initialization function that was exposed, and by calling that function you could kill the contract, and this led to, I think, $150 million being vaporized, basically. So they are now stuck in this contract forever. Nobody can ever access those Ether again. So just gonna show you a small video of how Mithril. So you run a myth analyze against the source code. And the output will be the sequence of transactions that leads you to the kill instruction, but it will also compute the instructions in a way that the remaining Ether gets sent to your account, right? So if you call set allowed, and in this case, that beef represents the attacker's address, you would replace it with your own address. In the second transaction, you call kill to kill the contract, and then you can see that this first argument specifies where the remaining Ether should be sent, and that's also the attacker, that beef. So if you just replace this with your own address, you will get the Ether out of that contract. So that was a very simple example, but Mithril can also solve more complex stuff that goes deeper into the contracts. And so if you get started in Ethereum security, a very good idea is to check out CTFs and challenges. And some of the best are Ethernaut, done by Open Zeppelin, Capture the Ether by Steve Marks, and the Blockchain CTF by Security Innovation. And I just pulled a couple of examples to show how our tool can solve these challenges out of the box. So if you look at this code here, you can see that this is a little bit more evolved. So we have a withdraw function that withdraws the contract's balance to the Ether. And we have a contribute function where somebody can contribute a little bit of Ether, and then some mappings will be set, and you will be added to this mapping here. And then there's a fallback function. Fallback function means a function with no name that gets called when none of the function signatures matches. And this may override the owner with your address. And there are several ways of how you could exploit this, but there's one way that is most profitable, right? Where you send the least amount of ether for the most output, and Mithril can compute it for you. So I will not show the video now. I will just tell you what you have to consider when running Mithril here. So the first thing is that this vulnerability is 3 transactions deep. And by default, Mithril only symbolically executes 2 transactions. And so the thing is, in symbolic execution, the state of space that you need to investigate grows exponentially. So the more you set here, the longer the analysis will take. And for like more real-life complex contracts, that can be quite a while, up to many hours or even days. So the default here is 2. And if you run it with the default, you will not discover anything here. So here you would have to set 3 transactions and an execution timeout if you want that will abort the execution if it goes over the timeout, because you might not be willing to wait a couple of days for a result. So what you get here again is the correct transaction sequence to maximize your profit. And what you do is you contribute exactly 1 way, which is the very smallest denomination of ether. It's basically like a billionth ether or so. And then you call callback with 1 way, and then you call withdraw, and this will give you the whole contract balance. All right? So I briefly mentioned the state space explosion program. So look at this contract here. There's a lot of functions with dependencies on each other. And so what Mithril does, it executes smart contract code in iterations. And once you find a valid stop state, it will that use as a starting state for the next transaction. So you can see that the space of states to explore grows very fast. And for something like this that needs 6 or 7 transactions, it can be quite a while. And there are a couple of ways that we use to address this problem. The main way is pruning algorithms. So what we're trying to do is to figure out which paths are actually relevant to explore. That means, for instance, if you execute a transaction and the machine state at the beginning is completely identical to at the end, like if you execute a pure function or view, then you can safely discard that state, because running another round of symbolic execution will not get you any new results. We can also do reachability checks, so at each basic block we can check whether the constraints can actually be fulfilled or not. This also gives us a nice speed up. And the probably most advanced thing we do is to look at dependencies in between transactions. So once we execute the first transactions, we build a map of state reads and writes. And as soon as we come to the second transactions, we have some rules that allow us to discard a lot of the paths that we encounter. For instance, if there was a state variable that's modified in the previous transactions that is accessed somewhere along that path, we know we need to execute the path because we might be discovering new pieces of code or new behavior. But if none of these things is fulfilled, we can just not execute the path. Just to show you how this looks like. So this is a state space graph of a typical 3 transaction execution. And you can see execution here starts at address 0. And as we get further down, we will reach several stops. And one of these, for example, is here. Sorry for that. So if you look at this basic block here, you will see that execution starts from program counter address 0 again, and then you get this tree of exponentially growing states. And that's not a good thing because it makes execution really slow. All right. So with pruning enabled, you can see we can reduce the number of states quite considerably. In the example I showed you before, it's down by 62%, and this gives us a nice speed up. So we run some benchmarks on the SWC, the Smart Contract Weakness Registry, and we got speed ups that compound over time with the number of transactions. As you reach less stop states, it really gets quite fast, but that doesn't mean that it doesn't still grow exponentially. So we're still looking at a lot of other things we can do, including parallelization. So obviously we could use more than one core to run the analysis, state merging, which is one of the techniques used by Manticore, and function summaries. So that means instead of executing functions over and over again, you create summaries by looking at the constraints exposed on memory and storage by each function, and just reusing those instead of re-executing the code. And this creates more complex solver queries, but also speeds up execution and reduces the number of states you have to look at. So, sorry, I'm a little bit over time, so I will very quickly show you a demo of Scrooge McEtherface, which is the next tool. So what this tool does is it creates the exploit transactions created by Mithril, and it just sends them to the blockchain. And it gives you interactive CLI where you can tamper around with the transactions a bit. So this is Ganache, which is a local test node. You can see here you have several test accounts, and the attacker's account is the second one here. It starts with 100 ETH. So I'm not going to deploy to this test blockchain version of wallet library, which is actually the library I mentioned that was exploited in real life before. And I'm going to give it a little bit of balance, 5 Ether. So you can see it was created and the balance was deducted from the creator account. Now I'm going to set up Scrooge with the config init to connect to my local node. And so now this is really script kiddie friendly. So the only parameter it takes is an Ethereum address. It will automatically detect the exploit. So in this case, you can see the contract can be killed by anyone, and what you have to do is send this exact sequence of transactions. And you now get a class interface that you can interact with. You get a list of raids, and each raid represents an attack, and these raids have steps that you can either first manipulate or execute one by one. And so call function 1 with this argument, call function 2 with another argument. and then you simply call execute. So transactions have been sent, and it actually also checks if your attack was successful and if your balance has increased, and in that case it gives you a Boolean true back. So you can see the attacker now has gained 5 ETH, which is $1,000, I think, at the moment. Right. So that's our tool. Full screen. Demo. So now that you have this tool, you could imagine it would be very easy to use it and steal stuff, but unfortunately the Ethereum mainnet is a very tough environment and it's not all that easy. So if you naively use these tools, there will be a lot of people out to exploit you. One of them is front-running bots. So they will actually monitor the mainnet for exploits being executed. And Daniel is going to talk about that a bit. And they will try to preempt you and steal your exploit and execute it faster than you and actually make your exploit fail. And then there are also fake exploitable contracts called honeypots that, for example, might know that our tools have some false positives and they might make it look like they're vulnerable, but if you actually execute the attack, they won't, and they will just require you to send a bit of ether and then make your attack fail. And yeah, it's super dangerous. So going ahead over to...
Okay, so once again, I'm Daniel Luca. You can find me online at Clean Unicorn. I kind of felt like I have to be a white hack with Clean Unicorn. Dirty Unicorn was taken. But anyway, okay. So I have 2 tools I'm going to show you. The first one is Karl. Its purpose is to mass scan the Ethereum network and find vulnerable contracts. It will generate like local reports that you can reuse then. And the second one is Theo. It's more specific because after you find the vulnerable contract, you will actually find a way to, it will actually enable you to exploit that contract. So Karl, it does mass continuous recon. So that means that it watches the blockchain all the time. So you can start it. It will scan all blocks. It will scan all transactions and see if any of the transactions generate new contracts on the blockchain. And if they do that, it pulls up the code. It pulls up the state and finds and tries to find if it's tries to find out if it's vulnerable. It uses Mythal for that because it's written in Python. You can use the Mythal libraries directly. It does exploit generation and it also does exploit validation because sometimes there are vulnerable false positives, but it has a way to reduce the number of false positives. So this is how like the core of Karl. It uses, as I said, it uses the Mythal libraries. So you can do this yourself. If you know a bit of Python, you can import the libraries, start up the Mythal disassembler. You point it to an Ethereum node, and then you tell it to load from the address, the contract address. So that means it knows who to scan. And then you start the Mythal analyzer. It has some parameters that you can play with. For example, the timeout, the number of transactions, what modules to test. So for example, the default modules that I'm using is stealing ether and self-destructing contracts. You can create others, and there are already others available in Mythal. And it generates a report something like this. So for example, with this report, we have unprotected ether withdrawal. So there is the smart contract ID. Problem ID is like 105. I always forget this thing. So the severity is high because you can extract ether. And then it tells you some other information like what's the contract address, but you kind of already know that because you were scanning for it. the estimated gas usage, and a text description just so you have an idea of what you can do with it. At the end of that, you can see the transaction sequence. So what transactions you need to send in order to get Ether out of that contract. So it makes it really, really easy for you. The problem sometimes is that you find the transaction sequence, but it's kind of hard to make sure that that indeed works. As I said, sometimes there are false positives. It helps if you know assembler, if the source code is available, if you have all of that available, but even then it's still kind of hard. So there, Karl already has implemented a technique to help you validate the exploit. So it still uses Ganache. So just a small intro. Ganache is a local Ethereum development node. And it just generates a local network for you. Nobody else can connect to it, but it behaves exactly the same as the Ethereum network. So that means that you can simulate all of the transactions and see if that works. So how it actually does is that it forks the main blockchain and it sends the transactions to that. But when people usually hear forks, it's something like there is contentious forks. Like people are fighting. There are two communities and they want to develop the network in two different directions. Some think that one feature would be the best, others think that another incompatible feature would be the best. So what usually happens with forks is that the community splits into two, and then you have two different networks. If you know, for example, Bitcoin and Bitcoin Cash, or Ethereum and Ethereum Classic, these are two very popular examples. But what I actually use is like the technical part of forking the blockchain. So in this example, on the top part, you see the real blockchain. And let's say that Karl identified that in block 100 there is a contract that was deployed. And then I need to make sure that this actually works. So what Karl does is that it starts Ganache, and then it creates a different future for that blockchain. So for example, block 101 is local, it's only on my machine. The top one is real and the bottom one is local. So then in block 101 I can add my own transactions and see in the next block if indeed I exploited that contract. So this is pretty safe because you're not sending the transactions to the mainnet. You can actually see if you did a good job and exploited the contract, and nobody else can see the transactions, and nobody could front run you and nobody could do anything to you. So I have a demo of Karl. So in this example, I start Karl. I point it to Infura mainnet, which is a public Ethereum node anybody can use. And I also ask it to start from a specific block. I do that because I already deployed a block, a contract there, and I know it's vulnerable. Otherwise, most of the times you wouldn't see anything. I enable sandboxing, which is the forking technique, which creates the local blockchain and tests the exploit generated. And I also enable the output to the folder, just so in the future I can have a list of files with the exploits available. So it's scanning this block, it found the contract, it finds one issue, but it's also firing the sandbox tester. So in this case it's quite fast. You can see that you have an initial balance of 100 and you have a final balance of 101.1. So that means the exploit is valid, and you could use this and exploit the contract. This contract, I think it still exists on the mainnet and nobody's actually exploiting it, so I'm super sad about that. So what Karl does next is that it takes the next block, it checks the contract and scans everything. So it goes through all of the blocks. And you could just leave this overnight and come back in the morning and see if you found some vulnerable contracts. So the next tool is Theo. Theo picks up where Karl left off. So Karl just generates a list of contracts, but Theo can actually exploit them. So it is kind of an exploitation framework because it helps you do some kind of recon. You can check some things on the mainnet. You can run the exploit. And we also have some features that are front-running, back-running, or sandwiching transactions, and I'm going to go into detail about that. But first you need to understand what the mempool is. So miners exist on the mainnet, and they have a list of local transactions that were not added to the block yet. That means that these transactions, if they will be added to the block, they will actually start to exist. They will actually happen. Before that, they're not real. They are pending transactions. So this miner has a list of a few transactions, and then they receive from the network a new transaction. So that means that they will add it to their mempool list. What actually happens in the network is that you have all of these miners. People who want to send transactions to the network send to one random or less random node, and then everybody sends the transactions among each other. In the end, they all kind of have the same mempool, but not exactly. But the idea is for everybody to have as many transactions as possible, just to have them mined. The cool thing is that you don't need any permission to be part of the network. So if you look in the bottom part, you can see a hacker who can listen to the mempool and see what transactions will happen on the network, but were not mined yet. Another important part is transaction ordering. So the miners, every time they find a block, they get a reward. So they get some ether. But they also get some fee. Each transaction has a fee attached to it. And when they add that transaction to the block, they also get that fee. So they are incentivized to add as many transactions as possible and to have the transactions as profitable as possible for them. So the transaction fee is calculated by gas and gas price. The gas part is, for each instruction there is a number of gas added, so you need to pay for complicated computation. For example, if you do some cryptography, if you do some square operations, you will pay more than compared to a simple addition or a simple subtraction. So you have gas times gas price, and the gas price is set by the sender. If they want their transaction to happen faster, they will add a bigger gas price, otherwise they will have a lower gas price. So when the miner creates the list to add the transactions in the block, they will usually sort the transactions descendingly by gas price. And they will add as many as possible until they fill up the block. So in this case, we can see that the first transaction added has gas price 5,000. The second one is 2001. The third one is 2,000, and so on and so on. So front running happens, like the idea of front running is that you have an information about what somebody is going to do. In this case, you see what the mempool is has in there, but didn't happen yet, and you raise them and you do that action first. So in this case, the hacker can see a transaction. They see that a specific contract is called. The gas price of that transaction is 5,000. A specific method is called, and once they do that, once they see that, they can add their own transaction. So in order to front run, the easiest way is to just take the transaction, add 1 to the gas price. So that means that the miners, by sorting descendingly the transactions by gas price, yours will be ahead of theirs. So I have an example, but first I need to go with you through the contract. So we have a contract with 2 methods. These are the 2 important methods in this example. You can claim ownership, but the important part of claim ownership, so this transaction does 2 things. It accepts 0.1 ether, and you need to send that. And if the contract was not claimed by anyone, it will make you the player of the contract. The second transaction checks if you are the player of the contract, and if indeed you are, they send you all of the ether available in the contract. The cool thing is that if you're the first to do this, you will become the player, but if you are the second, you just add more ether to the contract. So I can show you a demo, and you can. What we did is that we made a honeypot out of this, and this is how it works. So in this screen, I have a local get node, which is the official Ethereum implementation. So it's just mining. It's just creating blocks at the moment. And in this screen, I have a local IDE. It's a web IDE that people can use to deploy contracts and test contracts. So I already have this contract deployed. It has, I think, 10 ether attached to it. And it needs 0.1 ether from the attacker to claim all of those 10 ether. Okay, so now I start Theo. I provide Theo the account's private key because Theo needs to have an account in order to send transactions. So it needs to be able to sign transactions and send them to the network. And then I also need to provide the contract. What it does now, it uses the Mither libraries, it scans the contract, and it finds the exploit path. You can also add your own transactions. So it found a vulnerable path. It's very similar to what Karl does, to what Scrooge does. So let's say, for example, Scrooge is trying to exploit this contract. So what I do now is that I just extract the first exploit, and I start front running. So what it does now, it's just scanning the mempool for new transactions. So it just looks at the mempool, it queries the Ethereum node every second or so, and it sees, it checks if any interesting specific transaction is added to the mempool that will be added in the next block. If that happens, we will see what it does. So now I'm simulating the attacker, or Scrooge. So I'm changing to 0xFFC. This is the attacker, or the script kiddie. He needs to add 0.1 ether. He needs to call claim ownership. So he's trying to extract that ether. He's trying to become the owner or the player of the contract. And what immediately happens is that Theo sees that transaction and it adds its own transaction. It increases the gas price just to make sure that Theo's transaction will happen before the script kiddies. The script kiddie will also try to retrieve the ether out of the contract. Theo also identifies that, and it's sending its own transaction, and hopefully at the end we will see more ether in our account. So Theo's account is 0x1df, the one that we see now. It's 110 ether, so it successfully exploited that script kiddie. So this was all done locally, and then we thought, what if it actually works in the wild? And we had to test it. And what we see here is that we deployed a very similar honeypot. And this is the victim's transaction. About an hour later, somebody tried to exploit the honeypot. We also added this contract source code to make it easier for them to exploit. They didn't know that something was up. And they sent a transaction with a very high gas price. I think they were trying to make sure that their transaction will get picked up really quickly. And so in this case, you have 261.12 Gwei. And the nonce and the position in the block is 1. And Theo's transaction was 261.13 Gwei, which is like the minimum necessary to front run the transaction. And the nonce was 0, and because we're like everything starts at 0, it was just before the attacker's transaction. So that means that they became the owner and they also got the attacker's ether. So there are cases when this actually works. You have to deploy your own honeypots and you have to design them in a specific way to make them vulnerable for front running. In our case, it also helped if we shared the source code. And a very interesting example that might have a bigger impact is with decentralized exchanges. So a decentralized exchange, it's something like a normal exchange, but it exists on the blockchain. So what you can do is that you can sandwich other people's transactions. So for example, you see that they will buy something, you buy just before they do, and you sell immediately after they bought. So you earn some money by doing almost nothing. And there are some cases where it fails. It's kind of hard to see what a transaction does if they use a proxy contract. So they use an app in between them and the contract that they're going to exploit. It's impossible to front run if the miner is the attacker and they add their own transaction. So that means that they don't need to add the transaction to the mempool first. Sometimes the Ethereum client decides to be unresponsive, but there are ways to defend against Theo. So you can create a contract yourself and make sure that at the end of the contract you have more ether than what you initially started with. And if you know that, you can also create the honeypot in order to not be to beat this too. So there's a lot of where you can fight a lot on the Ethereum network, and this is just like there are a lot of layers. So what I really want is that I think we need more hackers. I think there are not enough people who are hacking on the Ethereum network. I might regret this, but at the moment I feel like we need more of you guys to exploit the network and find more problems and just have fun. So we have some links here. So this is these are all the tools. They're all open sourced. Maybe one important thing to say is that all of the ether that we stole from the people, we gave it back. I think that's it. We are open for questions. I know there aren't microphones, but we're available immediately after this.